All right, guys, the long anticipated video is coming to you now. This is the video, the last two sections of this chapter on series deal with creating a power series that mimic other known functions, but they're not polynomials. So for example, our first example is going to have to do with the cosine function, the trigonometric circular function we all know and love as cosine. This particular section, of these two sections together, I have it neatly packaged in my mind as to how to do the videos. There's going to be three videos. One is going to be on the development and use of development of the MacLaurin series. The next video is about the Taylor series, and the third one is applications. Okay, so let's take a look. We'll talk about the development of this thing. Like I said, on 3 Blue, 1 Brown, the guy was going, his introduction to Taylor's series was, what's with this series, this polynomial that they use to approximate cosine at small angle values for this physics problem? And that was a great introduction. It's being used. Anyway, the story about the MacLaurin series is we want, for example, we're going to pick the number on the number line, call this the x-axis, and we're going to pick on the number 0. And what we're going to do is we're going to create a polynomial p of x that is equal to really a power series. And the idea, the constraint is this. We all know what cosine does. Cosine does his thing, he loop-de-loops like this and all that stuff, and he keeps going, right? Okay. What we're going to do is we're going to find a polynomial first and foremost that goes through that same point, which is 0, 1. Cosine of 0 is 1, okay? But then we're going to force this guy to have the same tangent value, which is, in this case, 0, right? The slope of the tangent, 0. And then, no more and then, right? And then we're going to have it also have the same concavity. So we're going to build a polynomial that way. What we're going to do is we're going to say that if f of x is cosine of x, and p of x is some sort of polynomial. Now I'm going to throw some numbers at you and some notation at you. C0 plus c1x plus c2x squared. In other words, I'm just giving names to the coefficients, and you can go as far as you want to go. Okay, the one he was using in 3 blue and 1 brown was basically only up to the square or maybe the 4th power. Okay, but the thing is this. What we want is we want f of 0 to match p of 0. And we want f prime of 0 to match p prime of 0. And we want f double prime of 0 to match p double prime of 0. And we want etc. We want the world, don't we? So we want these to match. Okay, so we're going to build a MacLaurin series from scratch, and away we go. The first thing you want to do is you go, well, let's take the function f of x, which is cosine x, and let's look at its variety of derivatives. It's actually a fun function to watch because f prime of x, the derivative of cosine, is negative sine. And the second derivative, the derivative of negative sine, is negative cosine. And the third derivative, you got it? You see it? What is it? Double negative, you get a positive sine x, yeah. And then the fourth derivative turns out to be, guess what? Cosine x again. And you know what's going to happen? It's just going to repeat, okay? All right, that's all well and good. But now what we do is we plug in our number. We're going to center it, as they say. We center it at 0 when it's a MacLaurin series. And so what we want is f of 0 to match p of 0, okay? Now remember, p of x is this guy right here, all right? So what is f of 0? Well, what's cosine of 0? Cosine of 0 is 1. So we want that to match p of 0. Well, what is p of 0? I'll put it this way. Okay. I'll put p of 0 is equal to, looking up here, it's c0, but then look, all the x's are 0, and you have the following situation. For our experiment to go well, we start off forcing c0 to be 1. In other words, when I plug in 0 into p, I get 1. When I plug in 0 into cosine, I get 1. They match. Okay, they share that first point. Now, as we're doing this, down here somewhere, we'll start building this polynomial. And you know what it does? It starts out as 1 plus, and now we're going to go for the next one. Okay. All right, so now we're going to go for the first derivative of p, and we're going to match it to the first derivative value of f. So we need to, it's going to get kind of squishy here, but we're going to go p prime of x. Here's p of x right there. P prime, the c0 disappears. We're left with c1 plus, watch this, 2c2x, you watching? Plus 3c3x squared plus, and that's what's happening. Now what I'm doing is I'm developing it. I'm not showing you this is the fast way on a test. That'll come. But right now we're just understanding where it comes from. So therefore, what we find is that p prime of 0, look. See all the zeros here for x still? Is now c1. Okay? So p prime of 0 is just equal to c1. Okay. On the other side, f prime of 0 is minus sine of 0 is equal to what? 0. And we want these two guys to match, the 0 and the c1. So that tells us that c1 is 0. So as we're building our polynomial downstairs, I'm going to write out the terms even if it's a 0 so you can see it. We're going to get 0 times x. That's our next guy. Okay, he doesn't exist. What's the next one? And you just go over this iterative process over and over and over again. So maybe this time I'll start with the f double prime. So f double prime of 0 is negative cosine of 0 is negative 1. Now that's one of our guys that we're going to match. We're going to match that up. But is it going to be C2 or does it change? And the answer is, can you anticipate it? It changes, because if we go p double prime of x, that's a p, okay, we get the c1 disappears and we're left with 2c2. And watch this next one, plus, I'm going to write it in a funny way, 3 times 2c3x plus, and there's more. Okay, so what do we have? P double prime of 0 is none other than 2c2. Okay, so we want these guys to match, the minus 1 with 2c2. That's a 2, isn't it? Okay. So what does that tell us? It tells us that c2, this one's telling us c2 is negative 1 over 2. Man, we're going. So we've got a negative 1 over 2. Guess what? X squared. All right. And you can, all right, let's do a couple more, maybe one more. All right, let's look at f triple prime. Let's get some room down here. So f triple prime of 0 is sine 0 is 0. Okay, it's one of those guys again. Okay, so we're going to match up this guy. So whatever happens here, we are going to lose another coefficient because it has to be 0. So, okay, what's p triple prime? So p triple prime of x is lose the 2c2, and look what you've got. You've got 3, I'm going to call it factorial c3, plus this one is going to be 4 times 3 times 2 c4 times x. We didn't pick, I'm just bringing them into the play. Okay, so when we plug in 0 into the third derivative, what do we get? We get 3 factorial c3, and we want that guy to match up with 0. So it's telling you, okay, I got you. C3 is also, it's equal to 0. So we're going to go plus 0 x cubed. All right. Then the next one. Look at this. When we derive, and you can anticipate the answer, we're going to get C4 is equal to 1 over 4 factorial. Because cosine of 0 is 1. We're matching it with 4 factorial C4. They have to match. So we divide it over and we've got it. So we just start to see kind of a pattern. It's this. It goes plus 1 over 4 factorial x to the fourth. And let's take a look at this guy. So what we're going to say is this polynomial is, and you keep going, minus whatever. It's going to approximate the function f of x is cosine of x, because what we're forcing are all those derivatives to match. And that changes the curvature, the concavity, and it ends up wrapping the curve closer and closer to the cosine curve. It is an amazing process. It's really useful. So what we have is this. We have cosine of x is going to be approximated by 1 minus x squared over 2. I'll call it factorial, watch, plus x to the 4 over 4 factorial. And then you start to see a pattern. Okay, this is actually the MacLaurin series for cosine. Okay, what they do is they also wrap it in like summation notation. N is equal to, let's see how that works. It goes from 0 to, I think, infinity. And then what you have is a minus 1 to the n, and then you have x to the 2n. So you double the power. Okay, you double 0, you still get 0, with 0 power, which is 1, over 2n factorial, and that's the way that goes. Okay, so that's, I know you guys are working on this stuff, and that's how you get the MacLaurin series. There are theorems that say, hey, we can prove in a higher math class the remainder of the series, if you go out 8 terms, is this, or not what it's equal to. We can show you that the remainder is bounded by this number, and as you keep adding terms, it shrinks to 0. So technically speaking, this series approaches cosine of x. But I wonder if it works for all x. Okay, does it work for all x? Well, we've got a nice series here. We think it's cosine, but what numbers can you plug in? Remember the other series, 1 over 1 minus x, only worked for minus 1 to 1? Let's check the ratio test to see what the interval of convergence is, shall we? So we're going to take this guy and run it through, and we're going to say lim as n goes to infinity. We're going to take I'm going to ignore the negative. He melts away when I put absolute value around him. I'm going to take the n plus first guy, which is x to the 2n plus 2, right? 2 times n plus 1. And then down here, 2n plus 2 factorial. Flip it over, 2n factorial, all over x to the 2n. And we take this limit, okay? Looks like what we have is simply x squared up here. And if you know your factorials, watch, 2n plus 2, go down 1, 2n plus 1, go down 1, 2n, might as well keep going, call it factorial. Yeah, we're going to cancel the 2n factorials like so. And you're left with 2n plus 2 times 2n plus 1, like so. Forgot something. Lim, very important, as n goes to infinity. Well, as that goes to infinity, the denominator gets larger and larger, and x just stands there, and you get 0. What's the story on that one? Well, it's less than 1, no matter what x is. So the interval of convergence is minus infinity to infinity. It converges for all numbers. Okay, pretty cool stuff. All right. What I wanted to show you is I took a picture from Desmos, and I took, oops, there it is. I took this polynomial and I graphed it with cosine, and you get this mustache thing or whatever, right? So the blue curve is the polynomial. It's a 4th degree polynomial and has this loop-de-loop, and look at how it agrees right there. Really good. We centered it at 0, you understand, and so the farther out you go, the less it agrees. See that? See this here? But the closer you are, it's very good. Very good approximation of cosine. Hey, the power of this is we can use a polynomial. We can add and multiply stuff together to come up with values of cosine that we thought were off the charts. When I was a young lad, I thought cosine on a calculator, it looked it up on a table somehow. And that's not the case. It actually runs a polynomial. Really good stuff. Okay, so next video we'll deal with the Taylor series. I'll see you then.